We're talking about the lines of best fit today. The first graph that we see here forms the line, so it's a linear dependency. The second graph, what kind of dependency we see on the second graph?
It looks kind of like a parabola.
Looks kind of like a parabola, so we say we are assuming the dependency is quadratic, right?
Yeah.
What about the third one?
Oh,
This one.
that one's.
What is this? What does this look like from here?
I'm sure I see what the answer is.
Cubic, right? It looks like cubic. See, the end behaviors are different, right? And it's not linear, so it's either cubic or it might maybe it's quintic, right? Quintic. So this one will just say cubic. And what about the last one? What do you see here?
It's symmetrical.
Right, so what kind of dependency you see here? Quartic, right? Quartic. And so remember how we talked about special case of the quartic function? It can sometimes look exactly like parabola. So when you see parabola, this first one, it could be quadratic or quartic. But this one definitely looks like quartic. Why is that? What's the difference? It has three turns. See how it kind of has this wiggle in the middle. So it's definitely not parabola, it's quartic. Okay, good. So this we've done before, right? If we want to estimate our model using the calculator, we first make sure that our diagnostics are on, right? So that's important. Otherwise, we will not see those R's and R squares. We'll not be able to compare the models.
How do you check?
So you go second 0 to get to catalog. We'll do it. Don't worry about it. Okay, so enter data. We go to start edit. We enter our values as before. X goes into the first column, Y into the second column. And then we graph our data if you want to see the scatter plots, right? We don't always do that, but ideally you should do it. Just look at your data first before estimating. And then you get the equation. Start calc, and you choose what kind of model you want to estimate. Before we only estimated linear and quadratics, and now we will also look at cubic and quartic regressions. But everything else is the same. So to compare the models, you are comparing either R or R squares. R for linear, R square for quadratic. R is called correlation coefficient, R square is called goodness of fit. So the closer your R or R square is to either 1 or -1, the better the line fits your data.
So that's kind of like line of best fit.
It is exactly. These are the lines of this.
So do we put it in like the table? Like
Yes, we'll do it.
L1, L2?
Yes. So always the last line of calculator gives you either R square or R. Okay, so now we'll go through some examples. Questions here? Done this before, right? So let's just look at this first example. Determine the equation of best fit. So I get my calculator. Let's everyone just go through these steps to set diagnostics on, even though your calculators probably already have that. So I go to second 0 to get to catalog. Right, and then I need to get to my D's. You either like scroll down, but that's a lot of scrolling. So you go alpha D. And for some reason, this doesn't ever work for me from the first time, the second time works. So and then you scroll a little more down to get to diagnostics on.
You press enter when you're on diagnostics on.
Yes, diagnostics on, enter again to make sure that it's done. See, that work done. Okay, so now we are ready to estimate. You go to start, edit. We enter our data. Okay, so our data points. The x values are -2, enter, -1, enter, 0, enter, 1, enter, and 2. And my x values, now I go to my y values. So -6, negative 2, 2, 7, negative 2. Oh. Okay, so my points are entered. Let's just look at the data, right? To look at the data, I go to second y equal to get to start plot. Yes, gives you the start plot. So then you make sure that the plot 1 is on, everything looks good. Now you go to zoom, and then the ninth option, option number 9, said zoom start. So that's what you want.
So after you put the data in, you go to click zoom, and then you go to 9.
Yes.
Okay. Why do you do that?
And then you have your plot. So what do you think this model is? Looks kind of like what?
This one. How do you turn your plots on?
Right, so,
Wire.
oh, that's it. You have enter, and then it's on. So you're done. Now zoom. 9. Okay, so what do you think this model is? Is it linear, quadratic, cubic?
It looks to be cubic or quadratic.
I think it looks like quadratic. Parabola is the facing down, right?
So,
Yeah, so you clear this. Yeah.
oh, and then once it's clear, then you go to, oh. Can you show me how to?
Yes, so start I want to see if it's okay. So you just didn't go through all the steps. Let me finish this and then I'll show you. Okay. So our model I think looks more or less like parabola. Not perfect parabola, but looks kind of quadratic, right? The parabola that is facing down. Everyone sees that? So let's estimate the model. To estimate the model, we go start, calc, and then we choose our model. So we will estimate everyone and we will compare the r's and r squares. So 4 for linear. Depending on calculator, you might need to click it, enter several times. So here is the model. We note our r. So for linear, I have 0.546. I make a note of this last number r. I go back to start, calc, I estimate quadratic regression. So I get the new model, the new r squared. So my r squared for quadratic is 0.7597. I do the same thing for my cubic. So cubic is 6. I get a model, r squared is even better, 0.9622. Let's see if quartic will be even better. So far cubic is the best, right? So I go start calc and then quartic is 7. Yes, r squared is 1. 1 means perfect. There is nothing better than that.
If it's -1, it's also.
Yes, either -1 or 1 means perfect. So quartic, x to the power of 4, r squared is 1. So that's perfect fit. So we take our model and we write that down. So again, the model, the top equation just gives you the standard form of generic quartic model. You need to take your coefficients from these numbers A, B, C, and D. So my model for this data, the perfect model in fact, is y equals -0.67 x to the power of 4 minus 1.17 x to the power of 3 plus 1.17 x to the power of 2 plus 5 0.67x plus 2. And that is our answer. Questions? Usually we want you to round the coefficients to the second decimal. But we will look at one particular problem where maybe that's not a good idea. But usually for the test and just in general, we want you to round the coefficients to the second decimal. Okay? Okay, see you after lunch.
What happened?
Do you go off the R or the R squared?
R. For linear, it's R. Okay, so we are estimating this model, right? So for linear, what did we get for R? R equals what? Say again, 0.285. Okay, and is it positive or negative? Positive, okay. What about quadratic? So this is x squared, quadratic. What did we get for R squared?
0.679.
Is it 0.6? Everyone got 0.6? Oh yeah, 7. Good. Then for cubic, what did we get for cubic?
It's a 1.
R squared is 1. That's perfect model. It's perfect. When you get 1, you don't even need to go anymore. But let's see what the quartic says. What the quartic says? Did we do it? Somebody said that it's the same, right? So Bill, what is the quartic? 1. So even if you go up to the fifth and next one, it will be 1. Why? Because if we look at this, R squared 1, right? If we look at this model, well, I guess I have to do it because I want the coefficients. Well, tell me the model for the cubic. Y equals what? What is the A for cubic? Huh? A for cubic. Did we estimate the cubic model?
1.8.
1 point what?
8.3.
8.3. Let's stop there. So to the power of 3 plus what is B?
2.5.
2.5 what? We always round. We try to round to the second decimal. So 2.5 what?
That's it.
That's it. Okay. So x to the power of 2 plus.
Negative 7.
So minus. Okay. Minus what?
7.3.
3x, and then what else?
Negative 5.
Negative 5, right? So now, anyone did the quartic? Will. What are the coefficients for the quartic model? Did you do it? Okay, so even if you do it, this is what you will get. You will get exactly the same coefficient for B, C, D, and E. The first one, A, will be 0. So when we estimate the quartic model, it will tell us that it's a perfect fit, but it will give us the first coefficient 0. So it will look like this. And you see that the models are actually exactly the same. Because 0 times whatever number is always 0, and 0 plus, it's like, not having anything there, right? You see? Do you see this? That these are exactly the same models? Questions? So if the cubic is perfect fit, then we could say the quartic is perfect fit, the next one is perfect fit, is just the leading coefficients will all be 0, right? Which kind of deducts our model to the previous one. Make sense? Oh, come on, people. You just eat sugar. Yes, it makes sense?
So which one do we use?
Well, I say you use this one because there is nothing quartic about this model, right? If you graph it, it will be cubic model. So cubic is your answer.
So you base it off of the
First one, yes, the first perfect square. Perfect R square. So whenever you get R square or R, either 1 or negative 1, the first one, the lowest exponent, that's your model. Questions? Yul? All good? Okay. So next one. Um, so let's try number 3. What is the R for linear model term? Okay, so we are estimating the model and the students are doing the work. Okay, so what is the cubic? Let's just do the cubic. Push few buttons. What will be my R square? What do we think it should be? 1. We expect it to be 1. Let's check. Is it 1? Yes, it's 1. And the two leading coefficients should be 0. Are they? Yes, so A is 0, B is 0 because we are eliminating x to the power of 3 and x to the power of 2. And the rest of the coefficients should be the same as in my linear model. So C should be negative 0.67 and ABCD should be 5.5, correct? Good. So if you go even farther and do the quartic, it's actually my key, I didn't check, but my key says error, which is okay, right? I mean, it's either 1 or it doesn't make sense to go even farther, right? So you might get an error, but it's only because we should have stopped here. The R equals -1, this is the perfect model, so you can stop. Perfect. Questions about this? Good. Okay, so we can estimate the last one. Let's see. Do we want to or should we skip it? Same steps. Are we comfortable with the steps? Yes. Okay, let's skip this one. Let's go directly to the word problems. So the first word problem. We have the production of the silver in the world in metric tons for different years, for 1950, 1955, 1960, 1965. Let X be the number of years since 1950, estimate the model, write the equation. Okay, so when I enter this data into my calculator, what should I enter for the X values? 1950, should I enter what?
0.
0, right? Because I want the X to be the number of years since 1950. Read the instructions on the tests. Okay, because model will be a little bit different. So for the year 1955, what do I enter? 5. For the year 1960, 10. For the year 1965, 15. Good. So let's enter this data into the calculator. So I go start, edit, here my data, then I enter. So I have 0, 5, you know, before you start estimating the model, always just double check your data. Like one wrong number will mess it all up on the test. Just like glance at it again. Okay, so I entered my data, I go to start calc, I will estimate all 4 models, starting with the linear. So the linear gives me R, which is 0.2697. Go to the next one, quadratic. 5 for quadratic. Okay, so R square is a little bit better. Oops, for quadratic. 4, 4, 2, 2, 9, so 2, 3. Next one, start, calc, cubic, x. Okay, so my r square for cubic is 1. Do I need to go further? I need to check quartic? No, there is nothing better than 1, right? So I can stop right here and right now. Okay, so I take my... Why doesn't it work? Someone tell me. Why isn't it working?
It moved over.
Moved over where?
There's a one more. From where you were writing before.
Oh, that's right. I see. Okay, so my calculator. Thank you. Okay, so I can stop here and my equation becomes y equals negative 267.90 x cubed plus, oh, those are big numbers, they're the same. That's interesting. I have different numbers here in the key. Did I enter something incorrectly? Do you have the same numbers?
No.
No, it means I entered data incorrectly. I told you to check and then I didn't check myself. Start edit. 0, 5, 10, 15, right? 0, 5, 10, 15. 62, 23, 99, 67. Oh, see? 7, 5, 0, 5. Oh, 7, 5, 0, 5. 0, 5. Oh, my data was wrong. Why didn't you tell me? Okay, so start calc 4, 4 linear. Okay, so my R for the linear should actually be 22. Okay, start for quadratic. 40, so quadratic, 4, 4, 5, 3. And then start for cubic. It's funny how it was 1 before, right, for grown data. Okay, so cubic gives me 1. Okay, so I'll take this one and override what I had there. Okay, so my actual model is 12.09 x to the power of 3 minus 303.52 x squared plus 1944.07 x plus 63.23. Now you have the same numbers? Yes, looks good. Okay, so estimate in year 2050. What should my x be for 2050? Aram. What should my x be? What is it? Somebody said something?
0.
What is my x? The number of years since 1950. Remember, we switched all these numbers to we transferred them to x. So what would be the x for 2050? Yeah, 2050 minus 1950, which is 100. Right? So don't forget to convert that x before you plug it into the model. Because it's the number of years since 1950, right? So for 1950 we put 0, for 1955 it was 1955 minus 1955, and so on. So I need to transform that x. Everyone with me? Yes? Okay. So now we take this x, this value of x, and we put it inside of x, or instead of x, into our model, correct? And that's how we make the prediction, right? Okay, so y of 100 equals, and then I need to substitute. So 12.09 times 100 to the power of 3 minus 303.52, 100 to the power of 2, plus 1944 times 0.7 times 100, and then plus the constant term 63. So somebody enter this into calculator. What is your answer? What do you have, Austin?
I got 9,255.
9,000,000 to
555.
55. I have 65. Do you have 5?
9255529.
Maybe we rounded differently. Okay, so 9255. What's it?
Another 5.
29 metric ton of silver will be produced in the world if the trend continues. That's our answer. Questions about this? Oh, no, I look at my key, and it's a little bit different answer because in the key we rounded to the first decimal point. So when you round on the test, either 1 decimal point or 2 decimal points, but be consistent, right? Round every coefficient to the same decimal point, so that like the numbers are easy to check. That will be important. And this is a rough estimate anyway, right? This is prediction. This is not set in stone. If the trend continues, this is approximately what we expect. Okay, so the next one, I want to actually look at this one because this one has a little twist to it. So let's read it. The table shows the time it takes a computer program to run, given the number of files used as input. Using a cubic model, what do you predict the runtime will be if the input consists of 1,000 files? So if you provide the program 100 files, it takes half of what? Seconds? Is it seconds? The time, or in seconds, right? So half a second to process 100 files. 0.9 seconds to process 200 files. 3.5 seconds to process 300 files. So we are interested in 1,000 files. How long it will take for the program to process 1,000 files? Okay, so let's get our calculators and enter this model or data. So start, edit. Okay, you have to pay attention now. If you go into any kind of empirical science or finance or something like this, marketing, this is important. So 100, 200, 300, 400, 500. Those are our data points. 400. Now, 0.5, 0.9, 8.5, 8.2, 14.8. Okay, so start. How? We are told to use cubic model, right? You don't even need to choose, so choose cubic, 6. The problem tells us what model to use. Okay, so we get our result. Our R square is pretty close to 1, so this is a pretty good model. Right, so we will just use it. Okay, so now look at those coefficients. If I write this model just as it is written to me right there, so y equals negative 2.5 e to the power of negative 8. Do we remember scientific notation? What does this e to the power of negative 8 mean? Jaden, remember? What does it mean, e to the power of negative 8? Yes, Dylan? Hmm?
13.
Yes, so it's like this number 2.5 multiplied by 10 to the power of negative 8. But that's what it means is your number 2 will be the 8th, on the 8th place after the decimal. So it will be negative 0.000000123456725. So this is the coefficient, right? X to the power of what? 3. Plus my b is plus, again, b has this e to the power of negative 4, so it's 0.0000126, something after that. And then plus c, this is my, or x to the power of 2, minus 0.032, and then x, and then plus 2.48. Right, so if I didn't round too much, this is how my model would look like. Usually, we don't want to deal with all of this nonsense, and we say, oh my god, this is like 0, right, the first one. So I'll just say y equals 0 times x to the power of 3. If we round to the second decimal, right, this is what I would do. This would be just 0, because it's so small. Then the second one is pretty much 0 if I round to the second decimal. So I put 0 x to the power of 2. And then I take minus 0.032x plus 2.48. So if I do whatever we used to do, round to the second decimal, this is the model that I get, right? Let's see. So if I get this model, right? And now I want to make my prediction about what happens when I give this computer program 1,000 files to process. What will my answer be? Y of the 1,000 will be what? This is just 0, right? This is 0, correct? So minus 0.032 times 1,000 plus 2.48. What is the answer? 34, right? 34, negative, not plus. So it will be, what is the answer? 32 minus 2, so it's negative 27, no, negative 29. What is it? Tell me. 32 minus 2, 29 point what? 5, right. So now, can you put this as the answer to this problem? Why? You cannot have computer program to run negative 29 minutes. Can you? No, it doesn't make any sense, right? So you need to go back and see what went wrong, right? Something is wrong. Either the model is not a good fit for your data. You cannot use it to predict anything. Or there is some kind of restriction, like look at this real life situation and see, like there is some kind of boundaries or something, right? Like something. But this one, I mean, it seems like I can give the computer program 1,000 files to process, right? Should be fine. I should be able to predict the time. So the third option, so either the model is best fit, but ours looks pretty good. R square is very nice. The second possibility is, are there any boundaries, restrictions? Doesn't seem like it makes sense to, 1,000 files, computer program, whatever. So the third possibility, when you round it, did you round too much, right? You see how we said this is 0 and this is 0? But if you think about it, we are talking about 1,000 files. Your x is 1,000. If I take this x to the power of 3, it becomes 1,000 millions, right? How many zeros? I have 9 zeros in that, 1,000 millions. If I multiply 1,000 millions by this number, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. I will get negative 25. So if I use this model as is, I'll have negative 25. And then here I have x to the power of 2, so 1,000 to the power of 2 is a million. 1, 2, 3, 4, 5, 6 plus 126. And then I get the same here. So minus 29.152. So the actual answer becomes very much positive, right? It's like 126 minus 25 is 101 minus about 30, so it's like 71 seconds or something. Makes much more sense, right? About 71 seconds. So that would be my answer. So you really need to think like if you go to your work, right, and you talk to your boss and say, oh my God, I'm making this much progress and my computer is so nice, it will take me negative 30 seconds to process 1,000 files. He'll look at you like you're stupid. You don't know what you're talking about, right? So make sure when you do statistics, you read the question, the answer, does it make sense? Okay? Good, are you with me? All I'm asking is, before you put the answer in the solution, box, read the question, make sure that makes sense. The sign, the number, okay, that's all I'm saying. Okay, questions about this? Good. Well, our class ends at, let's stop for a second and regroup. What do we do?